The topic of our presentation is application of Laplace transform into RLC circuits. First, we will start with RLC circuits. Next, we will explore Laplace transforms. Then, we will see the application of Laplace transforms in RLC circuits. Finally, we will look at RLC transient analysis. Let's look RLC circuits. In the beginning, we introduce three fundamental components: resistors, inductors, and capacitors. Resistor, denoted as R, is a component that dissipates energy, mainly in the form of heat. Its unit is ohms. Inductor, or L, is used to store magnetic energy. It resists certain change in current, and its unit is the Henry. Capacitor, or C, store electric energy and resist certain change in voltage. Its unit is the Farad. These three elements are the foundation of many analog circuits and are key to understanding the behavior of signal in both time and frequency domains. Now, let's look at two basic types of RLC circuits, series and parallel. In a series RLC circuit, the resistor, inductor, and capacitor are connected end-to-end in a single path. This means the current is the same through all components. However, the voltage across each component can vary. On the other hand, in a parallel RLC circuit, the three components are connected across the same voltage source. This time, the voltage is the same across all branches, but the current in each branch can be different. Understanding this configuration is crucial because they have differently in terms of resonance, damping, and energy storage. Second chapter is Laplace transform, which is useful for solving RLC circuits. We look at its definition first. The Laplace transform of t equals the integral from 0 to infinity of e to the power of negative st times f of t with respect to t. Another derivative rule. This property allows us to handle differential equations, which are common in RLC analysis, by transforming derivatives into algebraic expressions. The Laplace transform of the nth derivative of f of t equals to s to the n times f of s minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0, and so on. Now let's look at the Laplace transform of some special functions, which are common in RLC circuits. State function u of t minus a. Its definition is that if t greater than a, the value of the function is 1. If t smaller than a, the value of that is 0. The Laplace transform of f of t minus a times u of t minus a equals e to the power of negative as times f of s. Another good way to calculate is the equation that is the Laplace transform of g of t times u of t minus a equals e to the power of negative as times the Laplace transform g of t plus a. Another direct delta function. Its definition is that delta sub a of t minus t naught equals infinity when t equals t naught and equals 0 when t is not equal to t naught. The Laplace transform of delta of t minus t naught equals e to the power of negative t naught s when t naught is greater than 0.
Solving transient circuits with Laplace, where math meets engineering. I will walk you through the solution of a second-order RLC circuit involving a 12-volt DC source, 2 resistors, a 1 Henry inductor, and a 0.5 Farad capacitor. The goal is to analyze the current response I of t after the switch is closed and t equals 0. Initially, before the switch is closed, the inductor behaves like a short circuit, and the capacitor acts as an open circuit. Therefore, we find that both the initial current and capacitor voltage are 0. I of 0 plus equals 0, and Vc of 0 plus equal to 0. To analyze the system post-switch, I use mesh analysis to form two couples differential equations based on Kirchhoff voltage law. These equations involve the inductor's voltage current relationship and the capacitor's current voltage derivatives. Then comes the mathematical magic, Laplace transforms. Using the Laplace transform, I converted the differential equations into algebraic expressions in the S domain. This transformation simplifies the system dramatically, making it solvable by standard algebraic techniques. After solving for I of S, I performed partial fraction decomposition and then applied inverse Laplace transforms to retrieve the time domain solution. The current I of t is given by 2 plus 6 times e to the power of negative 2t minus 8 times e to the power of negative 3t.
Fourth, I would like to introduction RLC transient. In electrical or control system, we are often interested in how a system reacts right after something changes, like when a switch is turned on, when the input signal suddenly changes, or when the environment shifts unexpectedly. This immediate behavior is what we call the transient response. Now, this kind of behaviors are usually described using differential equations. And when we deal with RLC circuit, the situation gets a bit more complex because inductors and capacitors store energy. This energy storage leads to second-order or even high-order differential equations, which describe how current and voltage change over time. Traditionally, solving this equation, especially when we have non-zero initial conditions, like an already changed capacitor or a flowing current, can be very time-consuming or tricky. That's why we use the Laplace transform. It turns those difficult differential equations into much simpler algebraic equations and makes it way easier to analyze how system responds to sudden changes. So in short, Laplace is powerful tools for engineers when dealing with transient response. Example of transient RLC circuit. Let's start with a real-world application, the emergency lighting system. When household power is suddenly cut off, for example, during a blackout, the emergency light automatically turns on. It uses internal battery to provide temporary lighting. Such systems typically include power detection, battery charging, and lighting control. In this case, we want to analyze the transient behavior of the system when the light turns on. To do this, we will use Laplace transforms to model and understand the system's startup dynamics. Now take a look at the circuit diagram. This is a simplified version of the emergency lighting system. We are focusing on the RLC part in the LED startup circuit. When the relay switches, the RLC is connected to the LED lamp. This cases a transient current to flow through the circuit, and that's what we will analyze in the next part. Once the switch is closed at time t equal to 0, a 5-voltage battery powers the LED through the RLC circuit. At that moment, the system experiences a transient response, a short period of adjustment before reaching steady state. To analyze this response, we use the following value: R equal to 10 omega, L equal to 100 millihenry, C equal to 100 millifarad. Using Kirchhoff's voltage law, we get the time domain differential equation. Then we apply the Laplace transform to move into the frequency domain. Solving for I of S, we get this form is much easier to work with, especially when there are initial conditions involved. Finally, the graph shows the simulated current response after switching on the circuit. As you can see, there is an initial peak followed by damping oscillation. This behavior corresponds to an overdamped or nearly critical damped response, which is typical designs in lighting system. This is our information and links. Thank you everybody for watching our group presentation.